So we're going to focus next on ordered dictionaries. Remember that with a dictionary ADT we have find, insert, and remove operations, which are all key-based. So we store entries, which are key element pairs. But with an ordered dictionary, we're going to support a few additional operations. So with an ordered dictionary, we're assuming already that all of our keys are ordered, that they have an order to them. So they have some sort of external comparator. We have a way to determine which one is smaller or larger. So the keys can be anything, but they must be ordered. So we'll have all the same operations we had before with an unordered dictionary, but we'll additionally support some operations that are based on the order of a key. So for example, we want to not find an element based on its exact key. Maybe we want to find an element whose key comes immediately before another one or after another one. Or we want to find all of the keys within a particular range. And just like we did before, we'll return kind of a special indicator to say that maybe if we're looking for an item and it's not in our dictionary, then we return something to indicate it's not there. So how would we implement an ordered dictionary? So you should always, like when we're talking about a new data structure, think about how would you implement this? Given these operations, given what we have to do, how would you design a structure to satisfy all of these requirements? So just to kind of start off with a basic data structure, we could just use an array-based sequence, which is sorted by key. And this is called a lookup table. So we can insert an item in linear time. So we have to find, if we're maintaining an order based on key, for one, we have to maintain where this new item belongs that will preserve that order. But also, because this is array-based, we would have to shift over items in order to increase the rank of items that come after it. Similarly, if we remove an item, once we find the item we want to remove, we'll have to shift items to the left to decrease the rank of later items. If we were using a list-based sequence, we wouldn't have to do this shifting, but we'll see that using an array-based sequence will be particularly helpful for us in order to implement the find element operation. So we could find an element just kind of straightforwardly by checking for every element in this sequence, does it match the one we're looking for? But we can be a little smarter about it by realizing that if our sequence is already sorted, we can use that order in order to help us find an element faster. And the method that we're going to talk about today is binary search. So binary search is a method in which we are given a sorted sequence already, an array-based sequence, and we want to find a particular element given some key. But we know already that our sequence is ordered, let's say ascending order, so we have our smallest keys are on the left, the largest keys are on the right. So the idea behind binary search is that we start off, rather than scanning everything, we start off at some particular key and at some particular index, and we compare against the key at this index with the key that we're looking for. And depending on how they compare, if it's smaller or larger, we can immediately determine which side of our sequence we should keep looking in. So for example, let's say we were looking for the value 10, and here we found the value 7. Well, because this is ordered, we know that everything to the left of 7 is less than or equal to 7, and everything on the right is greater than or equal to 7. So since the value we're looking for is greater than or equal to 7, we know already it's not going to be on the left side. We don't have to check the left side at all. We can just focus on the right part of our array. So the only question is, which of these items, of the n items we have, we should compare against first? So the answer to this is we want to pick the middle, because if we choose the middle item, then that guarantees that for our entire array, if we kind of break this up as best in the middle as we can, and we compare against this item, then no matter which side we end up going on, even the worst case, none of these are larger than half the size of our original array. So we've essentially broken our array in half. No matter what happens, if we end up going to the left side or to the right side, we'll only pick one of them, but we can guarantee by picking the middle that both sides are no more than half the size of our original array. We're effectively cutting our input by half. This is known as a prune and search kind of algorithm. So prune and search. So this is a type of design pattern. We'll see other examples of this later, but the main idea here is that we're looking for some item, and rather than comparing against every single item, with binary search we can compare against just one of them here in the middle, and then use the result of that to immediately prune our search space and realize, oh, we only have to consider this right half. And then in that right half, again, we pick the middle item, determine how the item we're looking for compares against it, and choose to go either to the left or the right, and kind of repeatedly prune our search space until we're left with just one item to look for. So let's see how this would work. We're just going to kind of step through this algorithm to see how it works. So let's say we're looking for the key 52, and this is the sequence that we're given. Right? So this is ordered in ascending order. We've got 10 elements here. So in order to prune our search space, we're going to keep track of a low and a high index. So this is showing that our current search space goes from low all the way up until high. And so these are going to change as we realize that parts of our array we won't have to look at. So the first thing we do is figure out what is the middle point of our current search space. So this is the mid index here. So we're just taking whatever our low and high index are, adding them together and dividing by 2, and just taking the floor of that. That way, if this isn't an even number, we'll still get an integer. So we're going to take this middle element. So this is the index of that middle element, and then compare whatever is stored there at that middle index with the actual key that we're looking for. So if we already find that key, then cool, we can return that, we're done, we don't have to do anything else. But depending on if the key that we're looking for is larger than the one that we're at or smaller than the one that we're at will dictate if we should go to the left or to the right. So for example, in this instance, this key at the middle point is 41, and this is smaller than the one we're looking for, which is 52. So that means since 41 is smaller than what we're looking for, then everything on this part to the left of that key, and even including it, is too small. So we don't have to look there. We know 52 isn't going to be there. We just want to recur on the right half. And in order to do that, we're going to change that our new search space is, we know that the element at index mid is too small. And since we want to recur in this right half, we're going to set our new low to be this element right after our midpoint. So this is, here we're changing our search space. This is our new low and our new high. Our high stays the same. So this is what it looks like next. This was our new low and our new high. And then again, every time we call binary search, we're determining what our new middle point is. So this is the middle of the right half of our array. And again, we're looking for 52. We compare 52 to the element stored here. We realize that we are, in this case now, that the item in the middle is too large than the one we're looking for. And since everything to the right of it is also larger than this one, since they're already sorted, we know we don't have to check any of these later items. So when we recur, we're going to change our search space so that it only goes between these items. So we already checked this part of the array and ruled that out. We ruled out the item at index mid, so we're going to kind of shift this over by 1 and go to mid minus 1. That'll be our new high point. And our low is going to stay the same. But we're still searching for the same key, and we're still working in the same sequence that we were given. So we haven't yet found the key that we're looking for. And we're going to keep doing this until we either find the key we're looking for, or we realize that if this key isn't in our sequence, as we shift these low and high indices, if they overlap, then that means we've kind of run out of room of where we can be looking for this key. Okay, so the next time we do this, we had reduced our sequence now to, we're only looking in this part of the array. We calculate what our mid is, just low plus high divided by 2. So this is our mid, and then we compare our key to that one, 52. That is actually the key we were looking for, so we finish in this case. So we return whichever element is stored there. So I'm just showing the keys here, but remember these are key element pairs. Right? So this is binary search. So how efficient is this really? Well, we make a few recursive calls, but you'll notice that in each of these statements here, just checking, evaluating these ranks, low and high, these indices, or calculating what mid is, or determining if the key that we're looking for, k, is larger or smaller or equal to the key that we're comparing against, these are all constant time operations. Returning an item, this is constant time too. Evaluating mid plus 1 or mid minus 1, this is constant time. So the only question is, how many times really do we recursively call this function? Because that'll determine how many of these constant time operations we'll end up taking in the worst case. We start off with a sequence of size n. We have n total elements here. And then within the first iteration, we divide this sequence by half. So now, depending on which, it doesn't matter which way we go here, but the new sequence that we're working with is of size n over 2. So the question is, how many iterations, how many recursive calls do we have to make in order to go from a sequence of size n all the way down to a sequence of size 1? In which case, once we have just one element left, we immediately know, based on whatever this element is, we can compare against and determine, is this the one we're looking for? If not, if it's not, we're done. We can return the item doesn't exist. If it is, then we can return the item we're looking for. So we start at n, we repeatedly divide by 2, because we're repeatedly halving our input size until we're left with 1. How many times does this have to occur? So we start with n, and then the next iteration, this is our first iteration, the next iteration we have n over 2, this is our, let's say, 0th iteration in the first iteration. And then n over 4, n over 8, n over 2 to the power of whatever our iteration is. So at what point is this equal to 1? When is this equal to 1? So this is the same as saying, when is n equal to 2 to the ith power? So you've seen this before when we were looking at the runtime of some algorithms. So if we take the logarithm of both sides, we're left with log n is equal to log base 2 of 2 to the ith power, which is just equal to I. So the number of iterations we have is log n, big O of log n. So this will come up pretty often, so just kind of keep that in the back of your mind, that if we start with n elements, the number of times we'd have to repeatedly divide by 2 until we eventually reach 1, the number of iterations that this is log n. Or you could equivalently think about this as, if we start at 1, how many times do we have to double this repeatedly until we ultimately reach n? And that's also log n. So the total running time of binary search is log n. Okay. So this is nice. If we have a sequence which is already sorted, then we can find an element in log n time. This is better than just scanning and comparing against every item. So this is what our lookup table does. So we know that insert item is linear and remove item are linear, but we can find an element in log n time using binary search. So the reason why here it's so important that we use an array is because our binary search algorithm is working on a sorted array. So we are really using the power of indices there in order to determine, when we prune this sequence and we find it, kind of get rid of a part of our search space, we update those indices low and high to keep track of what the current part of the array that we're working on is. But this is really, this binary search algorithm is good. We'll see this applied many other times as well, outside of the context even of dictionaries. Just given a sorted sequence, how do we find an item efficiently in it? But this lookup table, as an ordered dictionary implementation, is really only good if we have a small dictionary, if n is small, or if these search operations are the most common thing that we're doing because this is the most efficient function that we have here. Whereas inserting and removing don't occur that often. So we're going to see a better implementation of an ordered dictionary in the next video, and that's using a binary search tree. So again, if you have any questions, don't hesitate. Please post on Piazza. Reach out, let me know. Or any comments or anything else. Okay, see you in the next video.